So, welcome everyone once again to the Pi Seminar series dedicated to advancements in scientific machine learning. Today we have with us Dr. Matthias Möller, who is an assistant professor of numerical analysis at TU Delft in the Netherlands. And he holds a PhD degree in mathematics from TU Dortmund University in 2008 and joined TU Delft in 2013. Matthias' research focuses on the development of numerical methods for computational analysis of PDE problems and the computer-aided modeling and PDE constrained optimization of geometric designs. His current research interests are numerical methods that combine classical numerical methods, in particular adaptive finite element and isogeometric analysis, with concepts from scientific machine learning. Next to the development of numerical methods, he is particularly interested in their efficient implementation on today's and future high-performance computing systems, which will integrate emerging computing technologies such as quantum computing. As a second research pillar, Dr. Matthias is therefore investigating algorithms for exploiting the expected potential of future quantum computers in numerical analysis and optimization applications. Today's talk in particular will be on the integration of isogeometric analysis with operator learning, which is called as IgANets. And in particular, we will be shown particularly the contributions in IgANets that can be interpreted as network-based variants of least squares collocation IgA, which was introduced back in 2020. And the current method also inherits the consistency and convergence properties as the foundational method. And we will moreover present or we'll discuss more on the software prototypes that enables collaborative creation and analysis of design across multiple end-user devices, including tablets and VR or XR headsets. So over to you, Professor Matthias, for the rest of the talk. Thank you.
Thanks very much, Siddharth. Thanks for this kind introduction and also for inviting me to give this presentation in your seminar. Well, you already said it. This is kind of the combination of IGA, isogeometric analysis, with operator learning. And the idea should be to kind of harvest or get the best things of both worlds. So if you think about IGA, and I already said it in the pre-discussion, this is not really nailed down to IGA. So IGA for me is a kind of extended version of finite elements. So whatever I'm presenting here can also be seen as kind of finite element nets, if you so want. And well, if you look at what IGA or FEM makes so special is there's a very rich theoretical framework. You have convergence theory, you have all these nice things that a mathematician and I think also engineers like about it, but they are relatively slow. Yeah, you have to always assemble the metrics or at least kind of be able to apply the metrics. And then a couple of years back, let's say machine learning or AI as the big new thing that revolutionizes everything, or at least that was the promise, came, and that is fast. But if you look at the standard techniques like the pins, the deep O-nets, and there are many more learning paradigms, they are very fast, but they either completely lack such a convergence theory or this theory is different. Let's say not the standard L2 convergence or H1 convergence theory. And that was a little bit this motivation for my team and myself to look, can we combine these two worlds and kind of, lift over as much as possible or as much of the good things as possible from the two worlds. So there are a couple of names that contributed to this in the one or the other world, or sometimes even both worlds. I'm not going through them, but I just want to mention that this is, of course, not all, or would not be possible without a team of people contributing. Let me start by deviating a little bit and mentioning a term that is often used, design through analysis. And I just cropped a citation from a paper. And the most important thing is here that in this paper, they say that and I'm now quoting this, the potential value of design through analysis was demonstrated by a significant reduction in structural weight of the project vehicle. And you might now think, okay, design through analysis, that is one of the terms that kind of repeatedly came up in the, let's say, IGA wave, so that it's somehow new, somewhere between 2005 when IGA came up and today. Actually, if I show you now from which paper it is and when this paper is dated, yeah, it's from 1977. That means that this idea that we can do a design or create a design through the analysis, yeah, kind of interactive design, something like that, that is much, much older than we often think it kind of came with IgA. And when you then further look into this article, again, 1977, so the computers were much, much weaker than the ones that we have today. You see that in this article, they already sketched most of the modern concepts that we use, let's say, on a regular basis today. So CAD, computer-aided design. Then they call it simulation-based analysis. We would call it CAE today. And they even spoke about interactive visualization. Well, in the limitations, so with the limitations that of the time, 1977. And what this paper then further stresses, it's not about describing, let's say, these techniques in much detail. It's more about the manner in which these techniques were integrated and applied in a design environment. That is the primary topic or focus of the paper. Yeah, so kind of already these design through analysis, interactive design, dates back to this very old paper. Why am I bringing this up? Because this is still the idea or the vision that we have in mind. Of course, now many, many years later, and with much better compute technology and also with much better, let's say, methodology. And what we want, and that goes a little bit back to what I said on the title slide, we want a unified computation framework, in which we can do both things. We can do rapid prototyping, design exploration, and thorough analysis. And the idea should be not to switch between two paradigms like PINS and FEM, but really to stay in the same paradigm. And the ingredients, and this is also a little bit how I structured my talk, the ingredients are volumetric cut, with really the focus on volumetric, not on the traditional surface cut. Reparametrization, then IgA for the, let's say, accurate in-depth simulation, and the rapid prototyping, the thing that makes things quick, physics-informed machine learning. So let me just go through it, what I mean by volumetric CAT. Normally CAT, computer-aided design, describes or designs everything in terms of surfaces. And very often you have a couple of surfaces which are trimmed away, and then it looks like a volume, but it's actually hollow. No, what we really want for the design is a volumetric cut. What do I mean by reparametrization? Well, the cut people typically don't care about the quality of the parametrization. It just has to look like a G. This, for example, would be a G. From the outside, it looks like a G, but if you would look here, so if these would be elements, as said, IgA is kind of a special type of finite element. If you would consider this a finite element mesh, no chance that you do a good simulation on it. So the reparametrization or the generation of a good so-called analysis suitable parametrization plays a crucial role. Well, then IgA, I talk about that in a little while. So that's our, let's say, honest simulation engine. And well, rapid prototyping with physics-informed machine learning, that will be a kind of special network architecture. So what I will first do, because I'm not sure how familiar you are with CAT and volumetric CAT in particular, I will briefly talk about, let's say, this mathematical fundament, B-splines and IgA, then kind of smoothly blend from the IgA analysis to the IgA networks, and also discuss a little bit the implementation details, because I think, I also want to give some good practices that we figured out over the years. And then after that, kind of pitch a little bit how we put that together into a collaborative design through analysis framework. So when you look at what splines are, you figure out that they existed long before, let's say, the computer aided or the computational splines came up. So that was used for ship hull design or also then later in the aircraft industry. You just had wooden or plastic strips, what people called the splines, and they got fixed at several positions. So they got fixed at the two endpoints, and then in between at some knots. Well, the names for that were ducks or dogs or rats. I found in the literature that was not unique. There were not unique names. And then, according to energy minimization, the strips bended, and then you had a very smooth, or to be more precise, the best possible or smoothest possible shape. And then you can imagine that this can be very much used for ship hull design or wings of an aircraft. And the same idea of having a way that with a few discrete points, so these are the discrete points, and then with energy minimization, we get a curve. The same idea also holds for the computational splines. So what we have here is, or are three domains. So this would be the parametric domain, kind of where everything starts. Let's make it simple. We have the unit domain from 0 to 1. Then we have a couple of basis functions that are kind of the building pieces for our curve. And then we have the physical domain where we have this curve. So now this blue curve would be the spline as before. And these control points here would in some sense resemble the ducks or the rats. With a small distinction, they are typically outside the curve. So here we have some interpolation points, but the points with which you control everything are really these red ones. And by moving around the red points, you can influence the shape of this curve. And you influence them locally. It's not that this point here would influence the entire curve. It kind of only influences over the support of the basis functions. And what you can also do that you see here, you can reduce the continuity of the basis functions so that you have, let's say, kinks in the curve. Because normally, these basis functions are of some higher order. And you might recognize this looks a little bit like the standard head functions from FEM, only that it is now. Let me go a little bit into the math. So if we have a knot span, that is kind of these are the points in the parametric domain that span everything. Then with also an old algorithm, the Cox de Boer algorithm, we can recursively generate the basis functions. So we start with piecewise constant ones. You could maybe see this as a piecewise constant dg, discontinuous Galerkin basis function, and then you recursively build up the linears from the piecewise constants, the quadratics from the linears, etc. And by repeating knots, so for example here, this is a not repeated knot. We talk about quadratic B-splines, then the continuity is C2 minus 1. So we have a C1 continuity there. We also see it in the basis function. If we are repeating knots, we reduce the continuity. This is C0. This is just continuous. And if we repeat it even 3 times, we get something that you could see as discontinuous. It's interpolatory. At the end points, at the start and the end point, it's interpolatory. Like in FEM or IgA in general, we have nice properties of these basis functions. They have local support. They are non-negative. That, by the way, we don't typically have in all FEM functions. And we have this partition of unity property, which is quite helpful for numerical methods.
Matthias, just one question.
Yes, sure.
This non-negativity property, does it hold even for high-dimensional basis function?
Yes.
Okay.
That is one of the, let's say, distinguishing features over Lagrange FEM, for example. In Lagrange FEM, already the quadratics would be partly negative, whereas here they are really all positive. And for example, if you would do mass lumping in higher order FEM mass lumping, to kind of build up the mass matrix and lump everything on the diagonal is not trivial, let's say. you need some special tricks. Here, you literally, because it is all non-negative, you can literally sum everything and put it on the diagonal. It will collapse the higher accuracy and the higher order, but it's at least
Yeah,
possible.
exactly. So when we do mass lumping, so basically that will reduce the order of accuracy,
Mhm.
right? Okay,
I'm
okay,
not saying that it's maybe the best thing to do, but it's not something that is impossible.
okay. Yeah, thank you.
Okay. So yeah, you asked also in higher dimensions. One way, and there are also adaptive ways to do it, THB splines, etc. But here I restrict myself to the simplest possible. We just take the tensor product of one dimension or univariate B splines. Yeah, then typically the parameter domain is just the unit square or the unit cube in 2 and 3D. And then what we see is the line space in which we kind of approximate everything is this. Yeah. So what is it? It's the 2 or 3 bi or trivariate B splines, some control points. Now, of course, these control points live also in higher dimensions, so in 2D or in 3D. Yeah, and the number of basis functions, yeah, as kind of number of basis functions in one direction times number of basis functions in the other. So the core idea of IgA is now that we use this kind of basis, tensor product basis in the unit, or sorry, in the parametric domain, and so-called push it forward to the geometry. Yeah, so if we want to represent this geometry, for example, we take the basis and then just take these coefficients, these locations in X and Y to shape this quarter annulus. Technically, an exact quarter annulus can't be described by B-splines, then we would have to go to NURBS. But in principle, this is the way how it's done. NURBS are just a little bit more complicated, so I leave them out here. And if this push forward is invertible, which is typically what we want to have, so you could say no degenerate elements, yeah, then we can always go back and forth between the physical domain, this one, and the parametric domain, that one, by push forward and pull back. Yeah, so they are ideally bijective. And also all other quantities, like, for example, a right-hand side. Yeah, so let's look at the rightmost one. If we want to prescribe a right-hand side or a load vector, one, of course, can do it with an arbitrary function, but I would say the best thing, or what also fits well with the IgANet approach, is to project this arbitrary function into the spline space and then describe it only by the discrete Fi values. Yeah, so that would then be not positional nodes, not like these ones, but values, scalar values. And exactly the same with the boundary values. Yeah, for example, here, if you have Dirichlet boundary conditions, then we only look at the control points and basis functions that are directly at the boundary, and then imprint the boundary conditions by specifying these values. Yeah, so this here is now not in the XY position. It should be seen as a scalar. Yeah, so this area here would be the scalar value deviating from 0. Yeah, and as you already see, you can really design, and by design I mean manually or visually design your boundary condition by playing around with these control points or control knobs, if you so want. Okay, and then what one does is with all this, so we have the geometry, we have the right-hand side, the boundary conditions, we solve the problem, let's say Poisson or whatever problem we want to solve, with either a kind of Galerkin approach, so a variational approach, or something called collocation IgA. And what I will now do is only focus on collocation IgA, because that is, let's say, the natural counterpart of the IgA nets. Let's look here. This is how one can derive it. So if we have a weighted residual form, we just take a residual. L here is a linear differential operator in the domain. B is a linear differential operator on the boundary. Yeah, so this could be, for example, Poisson's equation with a combination of Dirichlet and Neumann boundary conditions. Yeah, then we take this residual and weight it by some test function. And this test function here, this phi omega, is a test function in the domain, yeah, composed of k Dirichlet, Dirac delta functions, yeah, at some discrete positions xi, and the boundary residual is weighted by some psi omega, which, yeah, kind of are another sum of Dirac delta functions, yeah, or centered around points on the boundary. Yeah, so if we substitute all this here and then recognize that, exploit the property of these functions, we just get a sum over a couple of discrete points in the interior and on the boundary. Yeah, and if we now take into account that all these coefficients are really arbitrary, we just get a sequence of, let's say, pointwise residuals or pointwise equations in the interior. Yeah, so this is in the interior, this is on the boundary. Yeah. You could also say, well, collocation is just evaluate the strong form at discrete points in the interior and at the boundary. Yeah, but what I wanted to make sure is that there is some weak counterpart or variational counterpart, that it's not just ad hoc approach, but that it's really, well, coming from a weighted residual form. Yeah, and if we then substitute what we have for our solution, yeah, our solution is again in this basis expansion, we basically get a linear system that we have to solve for these unknown solution coefficient. Well, not all of them are unknown. The ones at the boundary, at the Dirichlet boundary, to be more precise, are kind of known. And one more thing to say, this is of course not a dense matrix. I just illustrated here like a dense matrix, but it's sparse, yeah, according to the overlap of basis functions. And if you look now, what requirements do we need, and why is maybe collocation IgA more popular than collocation FEM? Well, these basis functions need to have high continuity, because otherwise, think of Poisson, yeah, we would have a second derivative, and we are not shifting the derivative to a test function. Yeah, we just have trial functions, if you so want. That means our basis has to be, yeah, C1, C2 continuous, that we can apply first derivatives for, say, Neumann, and second for Poisson. Yeah, that's why maybe collocation FEM is less popular than collocation IgA, because we have this higher continuity. And another point that is also critical, in order to have a non-singular, so invertible system matrix, what do we need? We need that we have exactly as many collocation points as we have basis functions. And of course, we don't want linearly dependent, so all the collocation points must be pairwise distinct. Yeah, these are the two requirements. And there's one more thing that I just want to mention here, which is the technicality. So if you look at where the basis functions were defined, they were defined in the parametric domain, yeah, in, let's say, the 0, 1. And all these derivatives here are typically taken in the physical domain. And I'm also writing it like, well, L, the physical differential operator acting on a basis function evaluated in X, that of course doesn't work. So what one typically has to do is transfer the differential operators in the physical domain into differential operators in the parametric one. But I leave it out here because it's, yeah, it just makes the formulas more complicated and hides the core idea. Yeah, but just to keep that in mind, the differential or the equations, the terms here look more complicated than here. Okay, so let's first look at what do we gain, what do we lose. Yeah, this is Galerkin IgA versus collocation IgA. Quarter analyst, the solution is this, and the model problem is just Poisson. if we look here, the Galerkin error is very small. Yeah, so in the order below 10 to the minus 5, significantly below 10 to the minus 5. Whereas if we look at collocation IgA, the error is already visibly larger. Yeah, so here the red points. And what I should point out is, where do we collocate? So we collocate at the so-called Greville points, which are well-defined points in the domain. And if we then compare, let's say, how does the error decay? So what is the convergence rate? Let's first look here at this one, at the top right diagram. Yeah, so the IgA-G is always the Galerkin, or the boldface. The bold lines are, the dashed lines are the Galerkin, the bold ones are the collocation. And what we see, Galerkin, of course, converges optimally with order p plus 1, h to the p plus 1, whereas in collocation, we see it does converge, but at a slower speed. Yeah, and even and odds have let's say, a different convergence behavior. Yeah, so basically, it doesn't make sense to go to P5 because P5 more or less converges the same as P4, quartic or quintic. Where we do see that collocation wins is in the computing time. Yeah, so that is the bottom diagram. Yeah, you see that, well, Galerkin takes more and more time the higher we go with the order, whereas with collocation, yeah, we do see that it goes up, but not really that much. Yeah, so here we are already at 10 to the 9, whereas for the same amount of data, we are at slightly above 10 to the 4, where my mouse is right now if we go with collocation. So before we now blend this to a network, let's look at the influence of the collocation points. So we had before the Greville points. There are many, many other ways to distribute the points. One is called clustered superconvergence points. And what we see there, this is now comparing the one with the other collocation method, that by going from, and this is now the dashed line, from the standard Greville-based points to the SC points, we get not just in absolute terms, better convergence or lower error, but we also get a different convergence rate. Yeah, and also visually we see that the error is dropping if we go from Greville to clustered ones. And then a question would be, well, if it is not so easy to find the optimal position of collocation points, can we maybe just increase them? Yeah, maybe just add extra points where we see the error is large. And that, of course, doesn't work with the standard collocation IgA, because there, yeah, the matrix has to be a square matrix. But with least squares collocation, it does work. Yeah, so when we have more collocation points, then degrees of freedom. Yeah, so M1, M2 is again in the interior, that is M1, and M2 is on the boundary. Then we can't invert, but we can kind of solve the problem in a least squares, in a minimization sense. Yeah, that's what's given here. And that is not just, let's say, some heuristic. There's also some theoretical justification in some paper that was written and presented by Lin and others. They give some criteria under which least squares collocation IgA is consistent and convergent. And there are some technicalities, but the bottom line is that in each element, there has to be at least one collocation point. So what one can do is say, we, for example, take the Greville points, and wherever we want more resolution, we are adding points, or we're taking the superconvergent points and add more when we need it. Yeah, and when we now compare collocation, that is this one, with least square collocation, we see, well, least square also does converge more or less at the same rate as collocation, but is typically in the absolute offset better. Not really at the very beginning, but in general, the least squares is either as good for P4 or better for P5 or P3. And yeah, if we now look at, do we have to pay in terms of computing time? Well, a little bit. Yeah. So again, the solid line is the least squares, whereas the dashed one is the, let's say, regular collocation, IgA. We do pay a little bit, but not too much. Okay, so let me bring up again this formula, this least squares collocation formula, because this is our starting point for turning it into a network. If we now substitute all the basis expansions, yeah, so here, what do we do here? We are substituting our basis times the unknown solution. Here we are substituting how we write our right-hand side or load vector. Here the boundary conditions, here the boundary values. And one thing, because you might say, where is the geometry? The geometry is here. Yeah, so all these derivatives, derivative in the physical domain, we convert them into derivatives in the parameter domain. So there is the geometry involved. And what we do now is we collect the discrete, let's say, control points. Yeah, so here, this is literally a control point because it kind of modulates the geometry, but also, let's say this is also controlling the value of the right-hand side. This is controlling the value of the Dirichlet or Neumann boundary condition. And this, the solution is not controlling. This is what we want to get out. This is also the degrees of freedom from which we can compute the solution. And if we now compare this and give it names that we know from pins or from other, let's say, networks for PDE solutions, we recognize a PDE loss function and a boundary loss function, kind of very naturally. And then it's not so much of a surprise that our network looks like this. So it's not too exotic. It's just a standard feed-forward neural network with activation functions. The only difference is that at the input, these kind of discrete descriptors of our geometry, the control points of our right-hand side of our boundary conditions, and as output we have the solution vector. Then the loss function is the PDE loss and the boundary loss. We train it in the standard way up to the point that, let's say, our loss is small enough, and then we stop training. And you might now ask, well, what is the relation or maybe the difference with pins or deep O-nets? I would say one of the big differences is in pins and deep O-nets, for example, you say you input the position at which you want the solution and you output the solution value at that point, or derivative or so. And all these things, geometry, etc., are somehow hard-coded in the loss function. Yeah. Here we are never saying we want to evaluate in a point X or in a point whatever. Yeah. We always provide the entire problem description. We get the solution in terms of discrete DOFs out. And then if you want to know what is the solution in the point, let's say 0.5, 0.8, we evaluate this solution in exactly the same way as we do in FEM. Yeah, we just evaluate this basis expansion. And if you want to compare it to deep O-nets, one could say it is very much like a deep O-net, but instead of having both the branch and the trunk network, we are not learning the basis. We give the basis and learn the coefficients. Yeah, again, these coefficients relative to the basis. And another thing that one might think, okay, do we really need this separation between offline training and online evaluation or online inference? Honestly saying no. Yeah, one can also say I have a completely untrained network and I just use it as a way to compute my least square solution. Is of course a little bit inefficient. So what we typically do is we pre-train it. But yeah, one can also, if one figures out that for a particular configuration, the loss function is too high, one can kind of continue training on the fly, if you so want. So let me give you a very first validation of that for Poisson's equation. So 7 by 7 bicubic B-splines. The geometries that we have shown are these, what is 1, 2, 3, 4 different annealy. Here we always have Dirichlet 0 boundary conditions. On that boundary, we have from 0, 1 up to 11, and then it goes linearly down. And as load vectors, we have 0, 1 up to 11. And this was an early implementation in TensorFlow with a ReLU activation function. And what you see, let's say, visually, and again, this is for the pre-design. We don't care about much accuracy. It's really to get a quick evaluation. So this is one configuration seen in training, and this really looks exactly like the, let's say, solution we would expect from the problem. We also looked at an unseen boundary condition here. And you see it is perfectly at the 1.4 level. And then we tried some more things, an unseen load vector, an unseen geometry, an unseen right-hand side. And if I go back, if I stay here, this is qualitatively exactly how the solution should look like. So what we then did next is look at how deep should the network be? How many neurons per layer do we need to kind of get a good resolution? So our loss function was put to a 10 to the minus 12. And what I want to point out is here. So with a single layer, a single neuron, we get, this is 2D, 16 coefficients per direction. That means 16 squared for the geometry. With this very, very small network, we already get something like 10 to the minus 4, a little bit below 10 to the minus 4. And what we then see, it kind of stagnates. I think it's this one. At some point, the network can't do it anymore. If we then go further, this is now one layer and 1,000 neurons. So still a very shallow network, but with very many neurons. We get 64 squared in 2D degrees of freedom quite accurately. So this is, of course, not an in-depth analysis, but we wanted to get a feeling, do we really need extremely deep networks with extremely many neurons? And we see with quite shallow networks, we can already reach, I would say, engineering acceptable tolerances.
Matthias, just one question. When you say you're satisfying a PD loss, can you go back to a couple of slides where you are showing the network? No. Yes, here. So basically, your output is U1 to UN here, right? From the network.
Yes.
And now that output should satisfy the PD loss given by this green box. So basically, but that is a discretized loss. This is not in a continuous format, right? And that is one of the reason you can actually use ReLU activation function. Is it? Am I correct? Because if you're using the automatic differentiation, then I guess using I mean to find out the derivative term, ReLU will not perform well there.
No. I should say the last layer does not have any activation functions. So here this is kind of the unmodified output of the network. So all interior ones have ReLU, but I must say that in our current implementation, so the other results were the TensorFlow results were our first attempt. I think now we use fully differentiable activation functions.
Okay. But will that gives, I mean, will that improve the, I mean, have you seen the improvement in the error because of, differentiable activation?
To be honest with you, we did not, I think we tested it, but we didn't do it systematically. So I couldn't say yes or no with confidence now.
Okay. Thank you.
But we'll definitely do that. But the point is, let's say in order to train, I come to that in also a moment. In order to train, yes, we have to fully train it with algorithmic differentiation, the network and all that. But if you have trained it and then say, I want to compute, let's say, the derivative of my solution, that you don't have to do with algorithmic differentiation, that you do just by differentiating the basis functions. And so that's what I meant. We have the full power of FEM or IgA. Yeah, when you want a gradient of a FEM solution, you differentiate the basis functions and you still keep these solution values.
Yeah. I think you should then try also the adaptive activation functions where you don't have to worry about the particular form of activation function.
Yeah, I read about that. We have not tried that yet, but I think that would be very helpful to try.
I will send some of my papers after.
Okay. Thank you. No, that's really good. Okay, let me move here. Well, maybe in view of time, I skip this. This is basically what I said. So we only need to, we don't have to differentiate the network if we want to evaluate it. We only differentiate the basis functions. One thing, and this is now a little bit about the implementation details. So these, let's say, this Cox-de Boer function is by no means efficient. And we found an algorithm that we had to modify a little bit that does this very efficiently. Yeah, so here R is the number of derivatives we want. So if we want second derivatives, then R would be 2. D is here the order. And what we basically do is, yeah, this looks like these ratio of coefficient differences, but it does it in a vectorized form. Yeah, so here these dot and this division is kind of element-wise or vectorized division and multiplication. And so this is very easy to implement in, for example, PyTorch or TensorFlow or MATLAB, and is quite efficient. And just to show you how efficient it is, this is now the blue one are on a standard CPU. The red ones are on an older GPU. So we now also tested it on newer ones. And what you basically see is, let me take out one, for example, for D3, that would be the cubic ones. Yeah, so the more functions we evaluate at the same time, so the more we exploit the vectorization, the smaller the time per basis function is. Yeah, and at some point we see that the CPU is kind of saturated. It doesn't go down anymore. And yeah, the green ones still go down. Yeah, with the GPU, it is really lightning fast to evaluate these many basis functions. Yeah, and the red ones are on an ARM processor. It basically has the same limitation as an AMD or an Intel processor. And now we are, of course, not only interested in 1D univariate B-splines. Yeah, so what we need are 2 and 3D B-splines. And here I just repeat, we have a couple of 1D B-splines, univariate ones. And our F can be the right-hand side, can be the solution, is the tensor product of all these 3 times the coefficient. And if we now calculate how much memory that would be, yeah, so we would have a lot of, let me say, we would have this amount here as a factor times the number of collocation points. And during training, what do? Well, we train for many, many collocation points, of course. Yeah, so at some point, the memory requirement would explode. And we couldn't kind of do many different geometries, many different right-hand sides at the same time. Yeah. And yet another thing is that these coefficients are not really contiguous in memory. Yeah. So if you think about a 3D tensor, then, well, in the leading dimension, they are consecutively ordered, but then here we have jumps, and in the third direction, we have jumps. I try to illustrate it here. Yeah. So this is now kind of put all the different tiles of the tensor, and we have repeated jumps. So to me, it doesn't make sense to evaluate this full matrix and then multiply it with something that is anyway jumping around the memory. So what we then did is come up with an algorithm that exploits that we have a tensor product or a Kronecker product. So I here just repeat the definition. And there is a very nice property. So if we have a matrix product between two matrices that are composed of Kronecker products or tensor products, then if these two matrix multiplications are well defined, one can write it like this. And if we now look at, well, we have, this is a univariate matrix times a fitting identity matrix multiplied by this. Yeah, that would give us exactly the tensor product of, or the Kronecker product of our univariate B-spline in the one direction times the univariate B-spline in the other. Yeah, so this is actually what we would want to compute. We can mimic it as a sequence of matrix multiplications with the univariate matrices times some identity matrices. Okay, and what I do now is, this was for 2, now I have it for 3. And what we see here is these are the ones in the third direction, in the second direction, the first direction. And there is yet another nice algorithm that does this in loops. Yeah, so we start with f with this coefficient vector, and then we kind of loop over all the dimensions. Yeah, it looks a little bit complicated. What this reshape does is basically it just interprets the existing memory with a different shape. There is no copy, there is no physical reshaping. It is just as a kind of new view on existing data. Yeah, and then we multiply this reshaped f with only the B part, the univariate basis functions, and with all these identities, we don't have to do anything. Yeah, and then as an output, we get exactly what we wanted to have. So to repeat, we don't have to assemble the big matrix. We just do it, let's say, iteratively with 3 loops or as many spatial dimensions as we have through the univariate B-splines. And then if you look here, this is now for trivariate, so in 3D. Yeah, and well, look, we can go up to, yeah, we can go even further. But if we go to 5th order, degree 4, to be precise, degree 5, 1 million sampling points. Yeah, we are with a GPU still at the at a very small. These are nanoseconds per entry. Yeah, at a very small compute time. So we have implemented this into a software called IgANets, which is building on top of libtorch, so on the C++ API, because all the computations are quite heavy and relying on Python didn't seem like the best option to us. And then also developed some backend front end. So I think that I'm a little bit running out of time, but anyway, I want to mention that. So what we do have is a kind of backend.
You can take your time, Matthias.
Okay, great. Then, well, then I slow down a little bit. We have a backend that is kind of a server, and this server communicates with the front end via a WebSocket protocol. And then in this backend, we have the different models. And so since we allow me more time, I go back once again. We have these IgANets implemented here, but we also have a second, let's say that is our true IgA software, Gizmo, geometry plus simulation modules. We use it for reference, but also to do other stuff. I come to that in a second. And then all these models, the network models and the IgA models, are kind of connected to the server as individual dynamic libraries. And then with this front end, you can connect to a session, and you can connect from different devices. So from tablets, laptops, even VR. So in a remote presentation, it's always difficult to show VR. But yeah, I can maybe offline show it to you at some point. So with multiple devices and end users, you can connect to the same session and then do this design through analysis on the backend. And yeah, you can choose between the learning-based or the network-based solver, so to speak, and Gizmo. Before I come to this, I just want to show you two more things, yeah, because, well, if you do all this is kind of taken from the VR stuff or from this platform. If the user creates a surface parameterization, yeah, then typically, and I go back again, and yeah, you do something, you pull one control point and say, now the geometry looks good. But that's, of course, not a good parameterization for doing analysis. So what we implemented there, and that's where we use Gizmo, for example, we have an automatic reparameterization techniques that preserves the shape up to some tolerance, and then redistributes the control points so that what we see here is the scale Jacobian, a kind of quality measure. Yeah, before, again, go back and forth. No. Yeah, this was all one. Now we make it that here the quality measure is very large. Yeah, and now with this reparameterization, it gets more calibrated. And similarly, if you have a volume, yeah, the user doesn't want to modify the control points inside. Yeah, so you might modify this cube. I overdo it here on purpose. Yeah, I push an auto control points deep into the interior, would cross some of the other ones, and then we have also a reparameterization technique that automatically places the interior control points in a way that the push forward and pull back mappings are still invertible. Yeah, so these are the things that all have to be done, because otherwise the user can use it, but very quickly makes the geometry, let's say, analysis unsuitable. Yeah, let me go back here. So this was just a quick presentation of, let's say, this blending between IGA and deep learning into IgANets. Also quickly, how we started to put this into a collaborative design through analysis workflow, and what we are currently working on is multi-patch. So far, this was just one patch. A patch is, yeah, what you can map from a unit square or unit cube. And with some students, I work on a Navier-Stokes version of this. So yeah, with that, I would want to thank you. And if you have questions, please let me know.
Thank you, Dr. Matthias, for this amazing and informative presentation. So I'd like to request participants to, like, if you have any questions, like, please feel free to ask right now. Yeah, I think Lynn has raised hand, so please try to unmute. If you could just unmute yourself and introduce and just ask a question, that would be great.
Thank you for presentation, Professor. I'm still working with nurse right now, so I have one question. In the neural network you're showing, you have the input is your matrix, the right-hand side, and the force. So the geometrics here is that control point or coloration point, sir?
I must say that it was a little bit broken, the connection. Maybe it's just on my side. What's the question? What is the input? Control points or the collocation?
Geometrics using the control point or collocation point.
No, it's really the control point. So it is these boxes. Yeah, so these control points here and here, these are the inputs, and these are the outputs here. And the kind of the sampling points, let's say, are hard-coded or could be hard-coded in the loss function. You could also have a switch. Well, actually, we do have it that you say, well, now oversample, like take final collocation points. And what we currently work on is do that adaptively. Yeah, so you calculate this loss in the collocation points. And if you figure out, okay, here the loss is very high locally at some points, then you can adaptively add more sampling points. Yeah, but the thing is, that is kind of in the network or in the loss function, and it's not an input to the network.
Oh, okay, thank you. Because I just wondering, like, because if the collocation point or control point is the most important in the training, so how can we choose which order we using, or how many number of the control point we using for the training? Because like you say, if we do in 2D, 3D, we will have more like the higher storage to using for the higher dimension.
Yes. So well, at the moment, we by default take either Greville or these super convergent ones, so kind of the standard locations. We also have the opportunity to say, well, take twice as fine. So do as if you had a refined geometry and then kind of use the collocation point, the Greville points of the finer one, but uniformly finer. As said, this adaptive switch that automatically detects where we need new collocation points, we work on that, but have not fully, let's say, finished and validated that. But if you look, let's say, if I still go here to this one, so this would mean I can do 1 million collocation points fully in parallel, and it takes, only a fraction of a second. So even if we have to do very, very fine sampling, so many collocation points, I mean, a single forward loop for the evaluation is still very quick.
Oh, thank you, sir.
So can I also have a quick question? So regarding the recent discussion on collocation points, so something that you discussed is like you adaptively increase the collocation point if you see that the error is slightly large at a specific region.
We work on that.
Yes. So what I understand is like collocation it's not an expensive process. You just need to throw in points during the training process. So may I know, like, is it in case if it is okay to discuss since you are working on it, so is there any decision? So what decision do you take, or how do you make the decision during the training process to adaptively increase or increase the localization of the collocation at a given specific region?
So, well, it's preliminary. The answer is preliminary. Of course, we work on that, as you said. At the moment, it's really where the loss function locally, say per point, is large or larger than a tolerance.
Right.
And I must be I'm honest with you, at this moment, the tolerance is user defined.
Yes.
There might be, or there are for sure better ways. There you could say, well, we just add, let's say, a regular, so not fully arbitrary, but kind of as if you would refine, and then there you add some control point.
Right. The reason why I asked is because, in some instances in the domain when you're training it, you might see that the error is very high, but in maybe a few iterations it might just steeply just reduce at a certain point. So if you make such decision before it actually happens, then so I was just thinking from the expensive standpoint, the computational standpoint. And like the other thing that I wanted to also check with you is like the memory thing that you mentioned when you're dealing with multivariate B-splines. So when you're dealing with the multivariate basis functions, so have you thought about the idea of like making it into vectorizing the tensor to make it more memory efficient? Because you told that every time it goes from one row to the other, it takes some time to switch between rows while you're dealing with a tensor. So I believe there are computational. I think I've dealt with like algorithms where people tend to like approximate matrices into vector-based formats so that they can easily go through the elements of the tensor in a more quick fashion when you're dealing with high performance computing, for instance. Yeah.
What do you mean by approximate? So you mean something like low order or not low
No,
rank?
the same elements would be represented as a vector. So basically, you will have a bookkeeping, or you'll memorize the address of these tensor locations, and then you will represent your tensor as a approximated represent it as a vector, not approximate, represent it as a vector, so that you have to just serially go through the elements rather than switching between the rows, which you told is more expensive when you're thinking about a vector tensor based computation. So just wanted to check with you whether this is something that was tried or looked into.
No,
Okay,
admittedly,
okay.
we have not looked into that.
Sure. Okay.
But that might be a good idea to make it, because we know that the data is very local. The XYZ
Right.
data is very local.
Okay. And one more question. Thank you for that insight. And the other thing is like when you're thinking about the IgANets, what I understand is like you are embedding the geometry by weighting the basis functions, and you're basically embedding the geometry into your input as an input vector. So does this pave way for more geometric agnostic approaches? Like you can have a network that is independent of the geometry, so that you just change the weights, and that would give you a new set of boundary and a new set of results. So is this something that is also tried out, or is it a new direction that you're trying out from your side?
Not sure if I fully get it. So what we do is, no, I didn't have it on slide. We train it for different geometries.
Right. Okay.
So,
Yeah.
and then, and there I'm also fully honest. Of course, you can't train it for 3 geometries and then hope that it can cover geometry. So but the way I want to see it, we try for a typical set of geometries for a particular application.
Right. Okay.
And then within these typical geometries and right-hand sides and boundary conditions, it should predict quite well the
Right.
output.
Okay.
Yeah, but of course, I do not believe that you can train a network once and then it will work for everything.
Right.
Yeah, so it's very, say, special purpose.
Sure. I think thank you.
I have one question, Matthias.
Mhm.
So basically, when you say you are training it on different geometry and predicting it on unseen geometry, so is it a interpolated geometry that you are predicting it on? Not some, I mean, you are not going out of distribution. Is it correct?
No. Yeah, it's correct. It's correct.
Okay. Mhm. And comparatively, I mean, compared to IgA alone, not IgANet, do you see any improvement in terms of IgANet in terms of the error, or they are almost comparable?
No, I would say quite the opposite. So the error is even larger than with standard IgA. Because I mean, there you really calculate, if you would stick to collocation IgA, you calculate the best possible, and Galerkin is even better than that. I think it's more the speed. Yeah, so I don't have it here on the slides, but I had a master student, and she did this comparison. Yeah, when does it pay off? And for a particular case where she did it for BEM, for boundary IgA, kind of, she compared. I do a couple of honest BEM IgA simulations, and I count the training plus the evaluation. And I think for this particular case, after 600 forward evaluations, the IgA net was faster than doing yet another, let's say, a 600th and first BEM IgA simulation.
Okay.
Yeah, but of course, if you do more training, then you might need maybe 1,000 forward evaluations. So I would definitely not sell this as a solution to compute once a PDE. Yeah, so it has to be embedded into shape optimization or something where kind of the training time can be gained back during repeated forward evaluations.
Okay. Yeah. Okay. Thank you.
Thank you.
Siddharth,
So thank you, Professor Matthias. So in case if no one has like any questions, I think I'd like to take this moment to like thank you for spending your time with us and discussing your research on IgANets. And it was very informative for me personally, and I wish to implement this sometime down the line in my research as well. So thank you.